Martin, over to you.
Thank you very much. Thank you also for the invitation, and it's a great honor for me to hold a lecture here. So today I will give you a short introduction, and it's more or less a helicopter flight into a topic who needs a long breath in development of parameters, processes, and also creating process chains. And also you have heard the lecture before me from Mr. Weinmann. So it is always a question of how to deal with your own development and your own approach. So first, a short introduction. That's the only advertisement slide I will give you here. You know Audi as a car manufacturer and the Volkswagen Group, so you can find some more information in the internet and advertisement clips. Of course, we as a metal 3D printing center are focused with 4 machines in 3 materials. We're producing development parts for the internal development processes and departments in Ingolstadt, but also worldwide spread at quarters of development. Also, we produce parts for production processes to enhance manufacturing and assembling lines, and also, and that's the topic for today, large volume tool segments for the forming processes. So you see some parts below. So of course, those are bionic designed or redesigned development parts. That's one column of our work, and the other one is the sector of tool segments. Very focused on the material in Ingolstadt. We are focused on the powder bed processes. For our side, it is more or less the most industrialized process in additive manufacturing for metals. Our colleagues in Wolfsburg using also binder jetting machines, developing processes there. So we don't buy any binder jetting machine for us in Ingolstadt. If there are any questions about these materials, we are in a deep exchange with our colleagues there, producing parts needed this processes or that processes or different materials. Then we have these very deep exchange of knowledge within the Volkswagen Group. That's also very important, and that's why we are so strong in the manufacturing of high volume tool segments. All right, so coming a little bit back to 2016, what I presented there, we had this, of course, approach to enhance the build-up rates of the machines, and we said, okay, there are some boundary conditions, but we will handle this, we will develop the processes, and we say there, okay, 500 cubic centimeters per hour could be happening in 2025, 28, something around that. Today we see, yes, we are mostly around here with 100 cubic centimeters per hour in our processes, in our machines, in our parameters. And why we are not in serial production? These are the questions of additive manufacturing. Also, these questions coming up always. Did you have any parts in serial cars, A4, A6? What is your opinion there? Of course, we know the processes of additive manufacturing in the powder bed. We know the advantages of these processes and the parts coming out from them. They are mainly used in prototyping processes. We deliver these very fast within 1 and 2 weeks. And for the manufacturing of parts in front of customer, for instance, interior parts, the surfaces are too bad, of course. We made some testings there over years, and we failed there, we have to say this. And also, if there is a manual finishing process needed, so the removement of the support structure, it takes time. And it is not only time, it is capacity, and it is cost related. So that's why we are not in serial production with AM manufactured parts. And one of these big columns is the manufacturing of hot forming tool inserts with conformal cooling channels. So you see a press line here, and also a little bit a picture of the process itself. So sheet metal will be integrated in a tool segment with 850 degrees and will be cooled down within 8 seconds to 200 degrees. So it is more or less a tool segment, or the tool system is a heat exchanger, and we have to cool down the parts along a defined cooling line and temperatures per second. So this is the B column and the A column of a car, for instance. These are special segments in the car body structure. They have to be strong and they have to be light also. So this is the this corresponding ends of a discussion. How thin could be a sheet metal formed part and how strong could it be? And therefore we use tool systems with a weight about 12 to 16 tons. And these segments, you see it here, are segmented in different segments. And therefore, for these segments, we print these tool inserts. And these tool inserts have a weight between 60 and 120 kilograms in the average. Okay, there are some pictures here. We're coming from a conventional cooled segment with horizontal drilled cooling channels, and the temperature on the surface differs because of the different, of course, distance to the mold surface or die surface. And with conformal cooling, we could reach a homogeneous temperature field along the tool surface, and we can also combine the advantages of additive manufacturing to lighten the segments from 60 kilograms to 30 or 40 kilograms due to bionic design. So the bionic design of these segments is not because we want to reduce the complete segment, the complete tool. It doesn't matter, of course, in a press line. But we want to reduce these segments by reducing the print time itself. So because we as an automotive company, we are cost driven, and the costs for such a tool segment printed are 3 times to 5 times higher than a conventional one. But the possibilities in the later on production processes and defining the best parameters for the metal forming process, standing for the AM process itself. So this is the design freedom of the part, also of the cooling channels, and placing the cooling channels. This gives us more freedom as in the conventional manufacturing methods. So that's the reason why we use AM. And this is, as I might earlier, the main purpose of AM for us. So, and of course, this is the process line and the process chain for such segments. First of all, there's a printing process. How to bring such huge and high volume parts to the printing machine. You see it here, it was really tough because of the distance between the build chamber and the surface of the build platform. So it scratched also a little bit on the wall, due to the heat distortion of the process. And of course, this was the first try. We have to exchange the build chamber. So it means we have also learned from the process and the process behaviors to optimize our own structures in planning and also in positioning these tool segments. So that's the first thing we have to argue there. There is a long development history in our house, starting from 2010. So we need more than 10 years to bring up these processes for these large tool segments. And then it's a question of depowdering. Also, Bernd Weimann has mentioned this earlier in his speech. So the depowdering of the cooling channels is very important. And the second step behind that, you need, of course, a special designed machine, and we have optimized and serial machine there, because a tool segment and the build platform weighs something around 150 kilograms. So you need a special machine there also. And also, if you are finished with them, with this process, you need a heat treatment. You see it here only as a picture. But in that case, you want to have the right mechanical properties in such tool segment, then you have the right print process, the print parameters, and also a heat treatment process with 2 steps, with your own temperature curve applied on these tool segments. So this is the special part of the process chain, and very convinced to the AM process, very special to that. And then the manufacturing, the traditional manufacturing starts. You can mill these segments. You can apply any surface quality as the conventionals could be there, and you can build up the tool system with these segments. Well, this is also the conclusion of that. You see nothing. Yeah? And also, everybody will ask, where is the segment placed? And the segment is placed here, and the surface and the corners between the segments are nearly the same as the conventional manufactured segments. So there is no difference between the AM manufactured surface after the milling process was applied to the conventional ones. Next slide, and this is why we do this. So there's a direct comparison in our press work between a tool system with conventional cooled segments and our 3D printed tool insert. And you see the difference in the heat transfer, and I say such a tool system is more or less a heat exchanger, and we optimize with these tool inserts our heat exchangers. And you see it here in numbers. So we see in the inlet and the outlet temperature will be shown that we perform better, of course. But this process needs also time on press lines, also the time and convincement with our guys who are using these tools, because it was a new technology for them. And right now we have a stable and standardized process based on these results for the next segments to choose. So right now we are manufacturing on our machine a 120 kilogram tool insert for the die casting process within 16 days. So machine is running, and the engineers and designers says, okay, if there is an advantage, we see that in our earliest processes to develop our systems for them, then 3D printing could be a possibility and will be chosen by them. And we, as a metal 3D printing centers, are the developer, and we bringing the ideas from the designers and engineers to fly, of course, yeah, because they say, okay, if I can have a better performing manufacturing process in the press line, then there is no discussion anymore to choose for AM. Well, so, and what I mentioned a little bit and shortly, there are sometimes huge differences in the heat, in the heat treatment of such segments. And as I underlined this earlier, we developed our own printing processes, and our machine technology enhanced this printing process, of course, to have a better cost structure, but also the heat treatment of our material printed along that what the pressworks want from us and also from our material. So this takes also time, and you see the results, a better result in the surface looking down in the material properties. So, coming up to a short conclusion. So, it is more or less also a discussion about process chains, the pre-process, the in-process, and the post-process. And of course, there are around 50 options you have to develop, and you have also to develop for your own purposes of these tool segments. All right. So, and this is a short introduction. This was a short introduction from my side in this topic. And if you have any questions, I will be here for some questions, and James will conduct this discussion maybe a little bit. Thank you very much.
Thank you, Martin. Yes, if anybody has any questions, I can run the microphone out to you. It was so comprehensive, Martin. You've answered all our questions. Well, even you. No, you haven't.
Good.
Hello, thank you very much for the interesting presentation. I have a couple of questions concerning the material. I don't know if you can talk about it. Concerning the material of the whole tool and the material of the segment.
The complete tool segments, the conventional manufactured are from 12367. That's the conventional one, or VP7 in German classification, and the printed ones are in 12709, maraging steel. So this is the, of course, oldest tool steel with less carbon due to the printing process possibilities, of course. We want to wish, that's a good question, maybe later on will coming up, we want to have other materials, of course, better corresponding with the conventional ones, but there should be a development in the print process and the print parameters, and also the own heat treatment strategy should be applied to that.
And then last question, you said you don't have any differential behavior between the, I would say, in terms of wear, abrasion, between the insert or the segment and the other parts. Everything is working quite the same with the tens of thousands of parts.
Yeah, so we manufacture with that part I've shown to you 1 million parts right now. So, and we have no other wear as we have on the conventional side. So this is also interesting. In the high pressure die casting process, 12709 is better and is slightly better performing as the conventional steels. So this is an advantage in the high pressure die casting processes for 12709. Yeah.
Thank you very much.
Yeah. Okay.
May I ask another? Hi, I wanted to ask about the bionic design you've mentioned. Yeah. Could you elaborate a little bit on that? Do you do certain kind of topology optimization? Do you calculate the strength and the wear of the tools?
Yeah, so this is one of the big topics. Calculation the forces of the press lines. So we have different press lines and also different tools there. And so the forces differs a little bit. But starting from that point, we simulate the forces on the tool segments. Then we apply the needed distance between the cooling channels and the surface. And then right now we are starting to optimize the weight. It is more or less not a real bionic design. It is more a weight reduction and an idea to reduce the weight.
Thank you.
Anybody else before we let Martin go? Yeah, one more.
Thank you for the very interesting presentation. I think it's in hall 12, there is a tool from Volkswagen Group on the Hermler stand. How do you see laser powder bed fusion sitting in that same area as these kind of spray-based processes? What's your opinion?
Yeah, we have an eye on that. Also, we develop our own processes there. So, and we are also in an exchange with them. So right now it looks that these processes could be cheaper, of course, but also they should be more development on that. So.
Still early.
And also, it's a learning process, of course. And the question is, in the terms of 12709 and our machines and our machine parameters, we can transfer these parameters also to a supplier if we have any hardware problems. Then we have a broad band of manufacturers and workbenches. And in that case, it is more or less in the research state.
Okay,
Right.
Martin, thank you very much. Thank you for your questions.
Thank you very much. Okay. Thank you, James. Okay.
Okay.